Hello, everybody. Welcome to the talk on high availability. Credit to Dave Rigby for the title suggestion. I'm Dave Finlay. This is Michael Nitschinger. We're going to go pretty quickly because we have a demo and a lot of stuff to get through. So we're going to go relatively fast. So without further ado, let's dive right in. What is high availability? So I do what people usually do on the internet. I went to Wikipedia to find out what it was. Your high school history teacher may not be that impressed with if you cite this as a source, but we have no such scruples. So anyway, high availability, it's a characteristic of a system which aims to ensure an agreed level of operational performance, usually uptime, for a higher than normal period, which it's a little highfalutin, but it's a reasonable working definition. But I think we can summarize it as saying systems that are highly available are up for a long time. So then immediately the question is asked, like, well, how hard is that? Is that something which is easy to achieve? And this amounts really to a related question, which is what can go wrong, right? So to find out a bit more about what can go wrong, I went to a higher authority than Wikipedia. This is a slide from Jeff Dean, one of the giants of distributed systems, from a conference that he presented at in 2009, the Lattice conference, large-scale distributed systems. And he talks about the first year of building out a data center. The data center is comprised of many clusters. Each cluster is somewhere between 4 and 8K machines. Let's say 4K machines. And in that time, the first year, they just took kind of notes on all the things that went wrong. So let's have a look at these. So some of these are just plans, right? Rack move, plenty of warning, but like 1,000 machines kind of get disrupted. Network rewiring, so 5% of the machines are kind of down over a 2-day span. Network maintenances, so these are things you can plan for. They're still extremely inconvenient. We can help you with them. So Couchbase XDCR is something that a lot of customers use to deal with these kind of eventualities. So you put up a new cluster, you XDCR over to it, you flip over the application to use that, and you can sort of navigate the pitfalls of periodic maintenance that is thrust upon you. Let's move on to data center level failures. So these don't happen very often, but they can really take you down, right? So overheating, probably multiple kinds of overheating. One kind of overheating you probably imagine here. Another kind of overheating is a fire, like fire marshal shows up and pulls the switch on your data center. You'll lose a lot of machines with very little notice. PDU is a power distribution unit failure. So you might have 1,000 machines disappear with very little warning. These are things that are difficult to plan for, obviously, by definition. But we do have capabilities that can help you with these, like Couchbase XDCR plus multi-cluster awareness can help you fail over your cluster kind of in real time. In previous incarnations of this talk at previous Connects, we've talked quite a bit about it. Most recently at New York and London, and then last year at Connect SV. Those talks are online, and the link is on the previous slide, actually. You can get out and check that out, and I think that's, if you have time to do that, that's well worth it. Rack level failures. So this is smaller scale, so you're not these big, horrible failures which just kind of take everything out. These are at a different level, but still extremely awkward. And actually, racks are kind of problematic because you might lose half of a cluster, or a third of a cluster, or a fifth of a cluster, and it'll be like that, right? So 20 rack failures, 5 racks go wonky. That's the kind of technical terms that people use when things go wrong. It's exactly how it feels. 3 router failures, like, okay, yeah, it's just very difficult. When nodes get partitioned off from one another, the node may be up, but like it's effectively down. And then lots and lots and lots of other kinds of failures. So it's sort of dominated by the other things, but actually these things are kind of worse because they crop up much more frequently. The numbers are much greater. So things like router reloads, DNS is out for 30 seconds. And when you're talking about fast failover times, which are in the single-digit seconds, like a DNS miss for this time can be problematic. Dozens of minor 30-second blips for DNS, 1,000 machine failures, right? Thousands of hard drive failures, slow disks, bad memory, misconfigured machines, flaky machines. And this is just the hardware. Like, there may be bugs in the stack that you use. There may be bugs in the kernel. These are not theoretical possibilities. They totally happen, and they're really annoying and difficult when they do happen. Okay, Michael.
Yes, thank you. So Dave talked about the quality of issues. There can be so many problems. Actually, one thing, if there is an unplanned rec move, I don't know how they would look like in a data center. Anyways, so how can we quantify failure? Or basically, how can we quantify measuring availability? And to do that, actually, I think we need to define two terms first. So one thing is the mean time to failure, and we can define the mean time to failure as basically the average time a system is up until it fails, right? And naturally, we want to make the mean time to failure as long as possible. But once we have the failure, we have the mean time to repair, and that's the time it takes us to bring the system back from a failed state into a non-failed state. What that means is really up to your application, right? It could be taking reads again, taking reads and writes again, or even like if one system is failed completely, like switching over to another system, right? That could also be another form of repair. So what it is exactly depends on your application. Now, and how can we define availability with those two? Well, we take the mean time to failure and divide it by the mean time to failure plus mean time to repair. Now, what gets immediately clear is that the mean time to failure is totally unimportant if the mean time to repair would be instant, right? Because if we have a failure, the quicker we can repair, the less we actually need to care about the mean time to failure. Now, one interesting case I've been thinking about this is, imagine you're building the Mars rover, right? So you're sending the rover to Mars, then you probably don't care about the mean time to repair at all, right? It's one special case where you want the failure to be as long as possible out there. Now, for us on Earth, I think it's really important to talk about those terms. And you need to be very careful to think about those numbers in a realistic fashion, because if you looked at the slide before, with all those failures, right, there are hard facts, you can look that up and you can see which numbers apply to your data center, right? If you have dedicated hardware, numbers might be different as if you're running on AWS, right? So again, to summarize, we want the mean time to failure to be big because that means less failures in a given amount of time. But once we have failures, we want to make sure that the mean time to repair is small, right? And we can help you with the mean time to repair, like things like rec zone awareness, automatic failure, but all those things that Couchbase has in place to keep the minimum time to repair as small as possible. Now, how do those numbers stack up? So there is the classical way of like characterizing availability is the number of nines in uptime. And when people toss those around like 3 nines, 4 nines, 5 nines, it's deceiving, right? Sometimes it's good to actually get hard facts on those numbers. Like, I mean, 3 nines, like downtime, 8 hours, 9 hours a year, that's probably okay. But once you go into the 4 nines and 5 nines, I mean, like 5-minute downtime in a whole year, that's pretty impressive if you can pull that off, right? And one other thing that's not on here is that if you consider modern architectures, like you have a database, you have an application server, maybe you have a load balancer in front of that, and the more services are part of your system, right? It's not, if you have 3 systems interacting with each other, and you want, let's say you want 4 nines of availability, like 1 hour downtime, you need to make sure that the services below have at least 5 nines of availability, right? Because if one of them fails, all the others are impacted. So basically the numbers multiply, right? They not add up unless you add them as redundant components, then you can make the math a little different. So having those numbers in mind and just thinking about it, like what does it mean to have an availability of 5 nines, 5-minute downtime, it's pretty challenging. Now, with that, I'll turn it over to you.
Thank you. So, you might be thinking, like, that's ridiculous. Like, how the hell can my system possibly survive in such an environment? And I think the answer we want to tell you is don't panic. We've got your back. So let's talk about achieving HA, and we'll talk about this briefly. Again, this is from Wikipedia. So the 3 ideas. Number 1, identify your system single points of failure and eliminate them. 2, reliable crossover. So this is reliable reconfiguration. When something goes wrong, when something dies, when a single point of failure or a singleton service dies, we need to be able to promote a new one. Or when a node dies, we need to be able to remove it and add a new one in a reliable fashion that doesn't cause downtime. And 3, we need to detect the failure quickly. So how does Couchbase help you do that? So let's look at a sort of a sample Couchbase cluster. 6 machines divided into 3 groups. So each of the servers is in a group, and so each group is going to be on the same rack. So this is what we advise. When you create groups, it should reflect the physical layout of your machine. So if you have 2 racks and you want to put 2 machines on each, you can create groups for these. This will mean that the data will be distributed in a way which is redundant. So when in Couchbase, we have partitions of the data. These partitions are called vbuckets. We have 1 active copy of the partition, and so for vbucket 1, which is shown here, the active copy is on node 1. But we've got 2 replicas in this case. This is imagining a bucket with 2 replicas, 1 on node 3 and 1 on node 5. And filling that out, now we can see our system has, in this case, it's a 6-partition system. We have more partitions than that, but this is fine for just elucidating how it works. So each node is carrying 1 active partition and 2 replicas, and the data is uniformly distributed. When somebody writes, so a user writes through the SDK, and you can see here we highlight the write coming to partition 1 by coloring that yellow. Then we see that the writes are immediately asynchronously replicated. Now, let's say a node should fail. I want to indicate this by the node getting grayed out. There are different ways a node can fail. We talked about that already. The data service itself could die. The data service could hang. The disk could get corrupted. The machine itself could simply drop. There's lots of things that could go wrong. But when we stop being able to communicate with that machine, we will promote and one of the replicas to take the place of the replica that we've lost. So in this case, we lost the active replica number 1, so we promote that. The rest of the system is left unchanged. One new thing in 5.5 is that auto failover is enabled by default. The reason for this is we see so many of our customers immediately. It's the first thing they want to do, so we decided that it's the right presentation for us to users is to enable it by default. Now, let's say later a second node fails. Now, in this case, we've lost node 6, active partition 6, so we need to turn that on node 4, and you can see that's highlighted. But now we've got 2 nodes down, but the system is still able to function because this is a bucket with 2 replicas. Multi-node failover, as shown here, is also new and is available in 5.5. In this case, this sort of tracks the idea of a rack failure. So here the entire server group has failed. So this is imagining we sort of went back and repaired our situation, and now a rack goes wonky and we lose group 1. So in this case, we've promoted the active partition on, oops, there we go. Sorry, let me just bring that back. We've promoted the active vbucket on node 3, and we've promoted the active vbucket on node 6. And this is also new in 5.5. Now, there needs to be an entity to make that decision. In Couchbase, we call that process the orchestrator. The orchestrator process is a singleton process that runs across the cluster. And it monitors the state of the cluster, and we'll talk more about that in a second. But when things go wrong, it is the process that will make the decision to fail over a node and promote replicas appropriately. But of course, this orchestrator itself is a singleton process, so it needs to be highly available too. It can't be a single point of failure. So when the orchestrator dies, we need to elect a new orchestrator to manage the cluster. And this is something that we've always done. However, there's been some interesting improvements to this in 5.5, which we'll talk about in a bit. Now I want to take you under the hood, just to give you a little bit of a flavor of what's going on, like how we do this. There's lots of interesting stuff here, but I'm just going to highlight this. So imagine we have a 3-node cluster. You can see the data service at the bottom. There's replication happening between the data services on these nodes. And the orchestrator is running in the middle node. So we have a data service monitor that runs on each of the 3 nodes. And it will check for all sorts of things. It checks for replication traffic. It checks to make sure the bucket's available. It checks also the disk issues, so whether or not the disk writes or reads are failing and showing issues. We have what we call the cluster manager monitor. So this checks to make sure that the cluster manager is functioning well. And this serves as a proxy for the node is working well. So for instance, let's say there's a network partition and you can't get to a certain node. That will get detected. That's measured because the cluster manager can't talk to itself. But if there are other services running on those nodes that are also impacted, it also captures these failure modes too. So what happens is that heartbeats are exchanged and information is exchanged between the nodes. So via the node monitor takes this information, all of the local visibility and knowledge of what that node knows about the cluster, and sends it to the orchestrator. So the orchestrator actually has its own view of the cluster, like what nodes it thinks are up, what nodes it thinks are having problems. But it also has the view of all the other nodes. This allows the orchestrator to make a more informed decision than simply, oh, I can't get to that node. Because if everybody agrees that a node is misbehaving, it's much more likely that it is, in fact, misbehaving. And this allows us to have a fast failover time. So the minimum failover time that we support is 5 seconds, which is actually really very fast. But having this robust failure detector that's able to look and see if there's synchronized information which indicates that a node needs to be failed over and then take action on it, reduces the probability of false positives. Can we do questions at the end? Okay. And what's new in 5.5 is the data service monitor. So the data monitor has been managing replication traffic, but what's new is it's now tracking read failures and write failures against the media on that disk. And with that,
thank you. So Dave talked about the KV layer mostly, right? So KV and cluster manager. Now, that's pretty important to get that right because, as you probably know, we are mutating data over KV. Now, we also have other services in the system, like cluster, index, full text search, and so forth. So here we're focusing on query and indexing. The good thing with query and indexing is that basically it's not mutating any data, right? So we can be more aggressive with going to other nodes and so forth. With KV, we have a very specific partition which is active, which we need to route the traffic to for mutation. Now here we have, again, the same cluster setup, 6 nodes, three racks basically. And on node 1, 3, and 5, we have the query service running. And on 2, 4, and 6, yeah, we have the index service running, right? So when you do a query, it goes to the indexer and so forth. So one thing we also support is index replicas, right? So you can define replicas for an index, and when an index goes down, the query engine will go to the replica automatically. So imagine the SDK is doing a nickel query. Here we have select star from messages where 2 equals Dave. So the message will be sent to one of the query nodes. In this case, it happens to be node 1. The SDK will basically do a round robin to make sure all of the query nodes are equally busy with serving requests. And then the query node will pick an index, and then we'll try to basically get the scan information from the index and then work with it. Now, what happens if node 2, let's say the index service is unavailable for whatever reason? Then the query service internally will know where the index replica is and go to the index replica, do the scan, and it won't be visible to the user level at all, right? So the SDK wouldn't even know that this index went down, and the user would also not know. Now, what happens if a query node goes down, right? The SDK has knowledge of all the nodes in the cluster, and if it can't access one of the query nodes, it will just transparently redistribute the requests through all of the accessible query nodes, right? So even there, as a user, you won't see any impact at all. Your queries will still be processed, right? So that's one of the great benefits of such a distributed systems with replicated services. We can not only scale with load, but we can also basically be more resilient and highly available in terms of failures. And with that, I'll turn it over to Dave for the demo.
Thank you. So I apologize if we feel like we're racing at 60 miles an hour. I think Art has us terrified with about trying to get leave time for questions. So I'm going to break out, and we're going to get to the demo. So we have, I think, 20 minutes, so we're in reasonable shape. So maybe we can relax a little bit and sort of enjoy the demo, because I think this is hopefully will illuminate the concepts we just talked about. Okay, so 6-node cluster. Can you guys? It's falling off the side. Let me just pull that in a little. All right. So 6-node cluster. 3 groups. So you can see we have group 1, group 2, group 3. And this is all running on my laptop. So everything is going to be, like all the 6 nodes plus the workloads all going to be running here. So it's kind of scaled down, but I think it shows how things work well. And this would be the same if we were running a 6-node cluster in AWS. But this is just a lot easier to manage. So that's why we're here. I created one bucket, the messages bucket. So very simple, not much going on there. And so let's start some workload. Oops. So let me just minimize that. So you can see here that we're running about 1,000 operations a second. So there's 670 reads a second, 330 writes a second. And this is obviously not a very big workload. The idea here is not to show the system running 500,000 ops a second, like the big demo this morning. We're just all smaller scale. But this will give you some sense of what your apps are like. Because I actually thought, like, well, for the demo, what I really want to show is I want to show how do the apps correspond? How do they manage through these failovers? And you might think that, I mean, obviously, we could certainly write an app for it. But one way for us to look and measure kind of the success of how we're managing the failovers is to look at the number of operations we sustain. Obviously, as nodes drop, the number of operations we're going to manage is going to be affected. So we want to see sort of a proportionate drop. If you lose one node, we would like to see an approximately proportionate drop in terms of our workload. That's going to look like, that's what it's going to feel like to the application. If you've got 6 nodes and you lose one, like 1/6 of your data is unserved for the time of the failure. And this comes back now, we want to repair that failure as quickly as possible so we can keep our availability numbers as high as we can, right? So, okay. And then this is workload. You know nothing about it. Let's look at a particular data item. So this is just let me just move this up a little so you can see better. So I'm going to post a message. This is just using one of our internal APIs. So we're going to post a message to our messages bucket, and it's the important message, and it's from me to Matt Kane, user ID 1, saying, I think the presentation is going well. Okay, so let's post that. Post important message. So posted. Now let's open up and see if we can find it. See if it made it. We go to Documents. I like the classic editor. Okay, so here's our message. Made it to the system, right? So is it going to survive a failure? That's our question. And to do that, what I want to show you is, so this is a command I wrote, and it just uses one of the tools that we ship with the product, which is the vbucket tool. And it tells you basically where your vbuckets reside. So I can make it a little bigger. Let's try that.
Can you read it in the back, or is it too small?
Well, it might be a little tricky. Let's try this anyway. So what you'll see here that it says master is on port 12,004. That's node 2. And you'll see the replica is on 12,010. That's node 5. And the second replica is on 12,000. That's node 0. So I'm going to run this sort of in the background. So you'll see here, as it's popping up, you'll see that we have a master and a full set of replicas. So let's drop one of the replicas and see what happens. We're going to drop replica 2. Oops. So now you'll see here immediately, this happens relatively quickly, we got node unresponsive. And now, boom, it's failed over. So that's fast, right? So what's the effect on our workload? Well, the effect on our workload is dropped a little bit for the period where that node wasn't available, and then the failover happened, and the workload came back. So this is So we had a partial failure. It wasn't a full failure. We didn't lose all service, which is kind of nice. And we didn't lose all. We only lost it for those 5 seconds. And that's kind of what you want to do. That's kind of how you want to handle it. So now let's look at another thing. This is new in 5.5. What happens if we lose the ability to write to, actually, let's go here. I just wanted to show this. So you can see here that we lost a replica. But that one of the object that we were writing to got promoted, or the vbucket that we were writing to got promoted, and now we still have we still have our data, and we have one more replica. But let's lose that replica. Let's lose node 5. And the way we're going to lose node 5 is we're going to just change the writability of the data partition for that node. So no more writes will be able to go through. This will get picked up by the data monitor, which will detect that now we don't have any writes. We've configured, the system is being configured to failover in the case of disk write failure. So we'll lose node 5. And that means that we'll be down to just one replica, one copy of this data left. So let's do that next. So let's make it a bit bigger. So change mode. So on node 5, we're going to remove, this is just a handy script that I wrote myself. It echoes the commands. You'll see what I'm doing in a second, but it just changes the writability on this directory, so I can't write anymore. And let's watch what happens. So here we go. So after 3 or 4 or 5 seconds, it'll pop up and go, write failure, and it'll fail over the node. There, gone. And let's go here. So we had a little blip, and you can see now we're down to no replicas. We got one copy of the data left. Now the interesting thing is our message still there, or is it gone? It's the moment of truth. So let's see, open message. Oh, we still have a message. So the last copy of the message. Of course, if we drop that node, it's gone. At that point, we're going to be gone. If you're in a lucky situation, you drop the node, maybe you can actually go and recover it. But if it's a disk failure, it might just be gone, right? So, but in this way, configuring with 2 replicas and supporting multi-node failover, we can actually survive these 2 independent failures to this point. All right, let's bring the system back. So I'm going to make it writable again. And let's go and restart the node here. Come back here. So you'll see as it comes back up, it says we can add back now. This is now. And this shows the reliable reconfiguration or part of it, right? So we can get the system back to normal, and we should have little to no impact on the workload. So just a little change in the workload as we're running extra load on the system. So here we're back to 1,000 ops a second, which we lost briefly during that time when the first node failed, and we had a little blip on the second node failure. Now we're back to normal. OK. I want to take you through another failure. This is, I think, an interesting one. This is an orchestrator failure. We talked about the fact that the orchestrator is responsible for these important decisions about deciding which nodes to fail over and which vbuckets to promote. Let's hang the orchestrator. And hanging the orchestrator is more difficult than simply killing it. If we drop the node that the orchestrator is running on, what will happen is that the other nodes will detect or if you drop the process, the OS process that the orchestrator is running in, the kernel will detect that node is gone and will actually close the TCP sockets associated with that process, which is a nice graceful way to degrade. All of the nodes in the cluster will be informed that those TCP site connections are gone, and it will allow us, begin sort of counting down the clock for when to initiate the failover. But if you hang the process, it's a little trickier. So let's have a look and see if we can find the orchestrator. The orchestrator is on node 0, a little tricky to tell, but the N0 at the front there tells us. So we're going to send a signal to node. Again, this is just a script I wrote myself. I'm going to send the stop signal. What this is going to do is it's going to hang the process. So nothing will die, no TCP connections will get closed. It will just sit there, not responsive. And this is the node that runs the process that's supposed to be managing everything else. So how do we handle it? Well, let's watch. So you're going to see a little bit of discontinuity in the way that we track ops, because the orchestrator is the entity that gathers organizes the gathering of the statistics. So you'll see a little bit of kind of discontinuity there. And you'll also see that it takes a little bit longer than it does for a different failover because we have to do two failovers. We have to fail over the orchestrator, and then the new orchestrator has to fail over the old one. Right? So let's watch this. So you can see that things have kind of stopped on this side where the stats are running. We're going to wait another second. Oh, that's back. And we go here, and you can see that now, look at this. The node 0, the one that we stopped, which is now sitting there, not doing anything, has been failed over. Don't worry, the stats look like we've lost something, but actually this is just the fact that the stat system is dealing with the fact that we've lost nodes and added nodes, and sometimes it's sort of lost context. But basically, we've had 1K ops through this whole process. What you'll notice, interestingly, is that it looks like we can still add it back, right? So it looks like it says add back delta recovery. You can't actually add it back because the node's unresponsive. The thing is that the Erlang system doesn't actually realize that this node is gone yet. This is the logs, and you'll see here that it says cluster manager did not respond for the duration. That's why we failed it over. And so what happens is eventually Erlang subsystem on which the cluster manager runs will recognize. And you can see it here. So now Erlang has finally realized that this node has passed what's called the net tick timeout, right? So this is usually a full minute. So actually, Erlang itself doesn't recognize nodes as down for a full minute by default. But we're able to, because of the way we orchestrate it, we're able to detect that. And we have to build in protections because it's possible, of course, that nodes can get disconnected for a brief period of time. And we don't want two orchestrators trying to fail each other over. So we've built protections against that. So each orchestrator will contact a majority of nodes before it executes a destructive action like doing a failover, which prevents possible dueling orchestrators. So it's an interesting thing. Anyway, so that's this. Let's bring our orchestrator back. So I'll resume it. So you can see all of a sudden we can add it back, delta recovery, and we'll rebalance it. And the last thing I want to show you is the rack failure. So this is something we talked about, that racks going wonky, right? So let's assume rack 3, which is captured by group 3, fails. So I'll drop 2 nodes here, come back, and you'll see again, and we're going to lose more ops. We just lost a third of our capacity, right? But what happens? Well, we will detect it, we'll remove them, and all of a sudden, we're back to normal. So in the case of 5, 6, 7 seconds, we're back to normal. So this is also very new in 5.5, and I think this is a very significant addition to our auto failover and our high availability offering, as coordinated failures like machines on a rack is a definite possibility, and it's something people see in production deployments all the time. And with that, let me skip. So just summary. I'm just going to I'll just leave the summary slide present, and I think we can pause here, Art, and move to questions.
So yeah, had you all worried you were ahead of schedule?
How many minutes do we have?
You've got 12 minutes.
12 minutes, okay.
You did really good. All right, so Q&A. What do we got here? Some great stuff here. Now, this isn't the time to ask Michael the question you're going to ask him later. You asked him the question later about the yeah. All right. There we go. Oh, your mic's not. Make sure your mic's on. Will be helpful if I turn it on.
So what's the difference between doing a delta recovery and doing the rebalance, as opposed to just doing a rebalance when the node just joins back the cluster?
So the difference is as follows. So the node itself, in this case, the node has previously been part of the cluster, and so there's data on that node. And what delta node recovery will do is it will contact the node, find out what data is there, and sort of minimize the data transfer to get it back in the cluster. And it's a strategy you can use to, if the node has previously been part of the cluster. If it hasn't, then it's not going to make any difference. But if it's previously been part of the cluster, you want to join it back, it may result in some time savings. It should result in some time savings when you join back. So it's part of Rebalance. What happens is before you click the Rebalance button, you'll say, I want to add this node back, and you'll have a choice of recovery options for the data service. If you say full recovery, it will simply rebuild those replicas from scratch. And if you say delta node recovery, it will find out where they are at, and it will build on top of the data that's already there, and you can save yourself some time.
What we observe is basically rebalance is always you have to rebalance somehow when the node comes back to cluster, because data recovery doesn't work that well.
We have to talk more about that. I think that.
Could you please repeat the question for the live streamers, please?
Sure. So the question was, it was a statement. Last part, I think it was a statement, and the statement was, we always need to add back full recovery because delta node recovery hasn't worked for us that well. I think we just need to dig into that to find out what issues you're seeing. What version of the cluster are you on? 4.6.
4.6.
Yeah.
All right, next question.
So you took my first question about what happens if the orchestrator goes down. Let's see. My next question is about how many maximum auto failures can there be? Is there like a formula to that?
We support up to 3, which is the same as the number of replicas, max replicas you can configure. So, we won't auto fail if it will result in data loss. And so if you have 1 replica and you have 2 failures, there's a good chance that you'll be left with no data for a given partition. And so in those cases, we won't auto failover in those situations. But if you have, in this case, we had 2 replicas, and I configured 2 auto failovers, and this is something you can choose, because obviously there's a capacity reduction issue here too. So if you start with a 10 node cluster, you can show up in the morning and have an 8 node cluster, right? In this case, because you've sustained 2 failures, and you want to make sure that your system can manage the load that at its reduced capacity can manage the load. So, but basically we support up to 3, but we won't continue auto failing if it will result in further lack of availability, because there'll be no vbuckets available for a certain partition.
So one of the things that we saw is when the failover happened, there is going to be read failures for some time. So what we have seen is if the number of documents in the node is too high, then the amount of time for which you see the failures is also more prolonged. Is that something that's expected, and what can we do to kind of minimize the time for which we see the failures in case of node failures?
Well, I don't know if I can repeat that. Was that captured by the? I don't know.
Yes,
Okay.
Yes, we captured that.
So it's very difficult to diagnose issues remotely on the stage. I think that when failover happens, you shouldn't expect operation failures for a very lengthy period of time. Michael can talk about how the SDK handles that. You want to address that?
Yeah. So basically, I mean, from an SDK perspective, it depends on what kind of failure happened, right? So if a node goes down, or if it dies, then the SDK won't be, as you said, right, access the document, like read it, right? So all of the partitions that are on that node won't be accessible to read and write. One thing you can do if you really want to minimize, and if you even can live with the auto failover, basically those 5 seconds, you can choose to explicitly read from a replica, but then you're choosing basically availability for consistency, so you could read outdated data, right, from the replicas. I mean, there's one option. The question in terms of if more documents are that it takes longer, I don't know. I think we would have to look at that, but it's not something that.
And I think the statement was something like there's too many documents on a node, and I'm not sure what that means precisely. So maybe we could talk about that afterwards.
Question about the orchestrator. So you showed that there is one orchestrator running. Mm-hmm. What about the redundancy? How do we cover the orchestrator if we are running and if something goes bad for the orchestrator, or it's hung, or something happens to it?
So that was the last part of the demo, or the second last part of the demo. So we hung the orchestrator. So the orchestrator was non-responsive And it wasn't a nice, graceful, non-responsive. It was simply just, we forcibly hung it. So we actually failed the orchestrator over inside the NS server process and promote a new one. We do that in around 10 seconds. Now, if the orchestrator died sort of in a graceful fashion, it would happen instantaneously. Or it would happen much more quickly. But in the case that I showed where we actually hung it, that's sort of kind of a worst case scenario, because how do you know it's gone if it simply doesn't talk to you anymore? So after 10 seconds, we give up, and then we will start counting. The new orchestrator will start counting down the old orchestrator and then drop it. So you'll have a total of about 15 seconds of failure detection. And it's kind of the worst case scenario. In most failures, you should see, if we've configured in this fashion, you should see a failure detection time of around 5 seconds and maybe another second or two for actual auto failover processing. So does that answer your question?
You showed us 6 nines, and you showed 36 seconds of the year. You took my 15 seconds out of that. I mean, I'm already dead in the water because my whole year is only 36 seconds.
Well, we didn't.
Sitting a 9,
Yeah.
5, 9, 6, 9 system. I have only 36 seconds to survive.
Right. I think that, what we showed was that there are different levels of availability that one gets to, and that as you get to the higher level of nines, your time budget is very short, right? I think that when you're at these levels, getting to 5 seconds of failover time is already very tricky, and the reasons are that these are read-write services, so we want to maintain the document consistency. If we fail over too rapidly, there'll be failovers happening all the time, right? If we fail over in, let's say, 200 milliseconds, you can imagine that sort of, somebody sneezes and you will lose a node. Once that happens, then you need to recover your cluster again, rebalance, and it's really not a manageable situation. So we need to balance the needs of the availability needs with the consistency needs. Again, it's a cap trade-off kind of thing.
Also, just to add up on that, like if you are in that category of like 5 nines, 6 nines, 7 nines, there are, I think, this is just one, like you need to build more layers of defense, right? If you are in that category, I think the trade-off there is also, like you need to throw more at it than just relying on this, right? You can imagine if you need that big, you can actually have another cluster set up, and then you basically talk to both at the same time, and if one of them happens to fail, you just take the other result, right? So I think there are other strategies. If you're at that level of availability, you need to have more layers of defense to actually deal with that, right?
Got it. Thanks.
All right. Go ahead.
If the host goes down or the process goes down, yes, it is fine. But if the host goes slow, basically, means instead of 20 millisecond, it is writing within 600 millisecond or 1000 millisecond, what will happen that time?
I think I guess we probably captured that question. So I think there are different things. So I think if you look at the data plane and the control plane, let's talk about the control plane first. If the control plane, which is really the cluster management system, starts to go a bit slowly, you really should see no effect on front-end operations, because essentially we have this separation between the data path and the control path. Eventually, either that will sort of remain, and it will just be kind of maybe a slow node, and that might be okay. You may eventually detect it because you may get timeouts with management activities if you're trying to gather stats from that node or something. And you may end up needing to investigate it. If it's on the data plane, there are lots of things that might start to happen. So you may start to get backup of requests. The SDK will start to maybe back pressure its ops. You might have replication buildup. That should be something you'll be able to observe in other nodes that can't replicate to it because it's right. You might see memory start to spike on those nodes, and eventually it may be the case that actually that it may cause a failure eventually. The degraded performance that you see on that node, this is really monitoring. And I think that there's different ways for monitoring to happen. There's monitoring capability in the user interface. There are stats endpoints that you can invoke to check that and find it out. And as an administrator, if you see that, you may want to make a decision to fail a node over that's bad, so you recover the performance on the data side. So that's how I'd address that.
But there is no way to do a auto failover on that case also?
Well, there isn't currently, but you can imagine how tricky that might be. How would you define the condition? How long does it need to be? And so on. We have no capability currently to do that, though. Right?
Hey, so thanks for all your awesome improvements to auto failover and turning that on by default. I had a question about auto add back. So we see a common failure scenario where maybe there's a switch outage and one of our servers temporarily disappears for maybe a couple minutes, something above the auto failover threshold. And then by the time a human looks at it, the node is back and we just manually balance it back in.
Yep.
Is it on your roadmap to do that automatically if certain heuristics are met to indicate that that is like probably a good idea?
So the answer is, I think, yes. So we are looking at that. I've been talking with some of the engineers about that recently, recent months, and I can't remember where we stand precisely on it, but it is something we're looking at. The issue is the heuristics. For instance, let's say the disk is bad, right? So you go through a period where the disk's bad, the nodes get failed over, and then you come back into the user interface and it looks like, please add back. It looks like it's healthy. You add it back and it fails over again. So there are reasons, there are sort of persistent reasons why one might not want to, certainly might not want to do it by default. In the case you described, yes, awesome. Like you add back is very nice. Bring the cluster back up to its full potential. So you haven't got capacity that's lost, and that's certainly something that would be within the capability of the system to do. It's the heuristics which are the problem part. How do you know it's not safe to do so? But I think we are looking at it, and we may do something in the relatively near future about it. But nope, I can't promise. But yeah, we're looking at it.
So how do you reset the auto failover count? Like in a setup with a one replica cluster, two nodes go down back to back in a sequential order. Is there a possibility of two failovers that trigger in, or?
Well, probably not. With one replica, unless your cluster is very large, there's a very good chance that the second failover will result in lack of availability for a substantial number of rebuckets. So we wouldn't fail over in that case, and we would sort of, I think, because there's no really good choice for the system to make automatically. A human needs to show up and decide what to do. Ideally, a human will provision a node, add it in, and rebalance, and we'll get back to full complement of replicas. Resetting the auto failover count is done via rebalance. So let's say you've got a 2 replica system and you've configured 2 auto failovers, and they both get processed. When you hit the rebalance button, then it will bring it back. It will reset the auto failover count to 0.
So you need to rebalance to reset the auto failover.
Yep.
One more here. Oh, there's one up. Okay.
So from the above demo, I saw that you have the index node, 2 index node, one in replica of the index. But usually we only have 1 index node. Mm-hmm. If that is done and the more data write in, so like later on when you bring the index node back up, how does the index node deal with the new data during the downtime?
Good question. So essentially, the index node builds its index from a DCP stream. So it will record the point that it reached, and then when it comes back up, it will read that point and go back to the data service on the different nodes and start streaming from the point that where it was. Now it will be a little bit out of date because it will need to catch up with the data that's a little bit ahead of it. But if you've got a single index node, that's how it would happen. So it won't rebuild the index from scratch. It will pick up where it left off.
All right, I've got time for one more question. Do we have one more question? All right, you guys are absolutely awesome. Terrific, thank you. Thank you very much.